All right, chapter 16. We've talked through a lot of things. We talked through pH scale, how to calculate pH, pOH. We talked about strong acids, strong bases, and then weak acids, and then how to handle that. So let's summarize some of this. First, it's the equations we started with the chapter, which are 1.00 times 10 to the negative 14th is equal to H3O plus times OH minus, which is the equilibrium constant expression for water at 25 degrees Celsius. We just plugged in the equilibrium constant there. So and we're living in a world where we're pretending like everything is 25 degrees Celsius. So we can always use this equation. pH is equal to the negative log of H3O plus. pOH is equal to the negative log of OH minus. And then pH plus pOH added together equal 14.000. So these are equations. Just a reminder for any of them that have logs in them, the way the sig fig rules work is the number of decimal places for the answer is equal to the number of sig figs for the thing inside of the log. Okay, so the pH or the pOH, we're basing it on decimal places, and the OH or the H3O plus, we're basing it off sig figs. Okay, so those are our equations. What I want us to do now are list the 7 strong acids and the 8 strong bases. Because you have to memorize these, and there's no way around it. Okay, so the 7 strong acids: HCl, HBr, HI, HClO3, HClO4, HNO3, and H2SO4. We just have to know that these 7 acids are strong acids. Now, 6 of the 7 acids, all of them but sulfuric acid, the molarity of the strong acid is going to always equal the molarity of the hydronium ion concentration. So if you know the molarity of HBr, you now know the H3O plus molarity, and if I asked you to solve for pH, you would just throw it into the pH equation, get your answer. It's glorious. Okay. So the weak acids we're going to talk about here in a second, but before we do that, oops, I want to change. Let's list the 8 strong bases and then talk about what that means. So the 8 strong bases all contain hydroxide. And there's a pattern for this one where there's not so much a pattern for the strong acids. They are the group 1 hydroxides and then 3 of the group 2 hydroxides. So group 1 metals, well, lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, calcium hydroxide, which calcium is a +2, so calcium hydroxide would have 2 hydroxides, strontium hydroxide, and barium hydroxide. And what this means if they're a strong base, well, that means they dissociate completely. So if we have a strong base that has 1 OH minus, so my first list, we know the molarity of the hydroxide ion. It's the same. Okay, the molarity of the strong base is equal to the molarity of the hydroxide ion. If we have a strong base with 2 hydroxides, its molarity times 2, is equal to the hydroxide ion molarity because 1 calcium hydroxide contains 2 hydroxides. So when it breaks apart and dissociates in water, we're going to have twice as many hydroxides as we had the original molecule. Okay. So in the last video, we talked about this. We did some examples of the strong acids and the strong bases of calculating pH from them. Okay. And then the other new thing that we learned in the last video was how to handle weak acids. Now, weak acids, we can identify them when we read the problem by being an acid, so either it has the word the name acid in its name, which is a big clue, or the chemical formula starts with a hydrogen. Okay, so that's the easiest way for us right now to recognize an acid. So if the chemical formula starts with a hydrogen or it has the word acid in its name, you need to look at it and decide, is it strong or weak? And the way you can tell that, you have to memorize the 7 strong acids. So if you recognize it as one of those 7, that makes it it's a strong acid. If you look at the chemical formula or the name and it's not one of the 7 strong acids, it's automatically a weak acid. So for a weak acid, they do not dissociate 100%. Instead, they go to equilibrium. Weak acids, I'm going to always represent as HA. That's the chemical formula that I'm using to stand for the hundreds or thousands of weak acids that exist. So when they go to equilibrium, this is what their equilibrium equation looks like. The weak acid, once it's mixed with water, goes to equilibrium, and the weak acid does what acids do. Acids, the Bronsted-Lowry definition of an acid is a proton donor. So HA is going to donate its proton. That proton is going to go to water to make H3O+, and HA, after it donates its proton, what we have left is A-. So this equilibrium equation isn't really rocket surgery. It's HA behaving like an acid and water behaving like a base. So since this goes to equilibrium, we can have an equilibrium constant expression. Now we are going to use for weak acids Ka to stand for the equilibrium constant. Products over reactants, like we learned in chapter 15. So H3O+ molarity over A- molarity over HA molarity. Now I ignored water because water is a liquid. Liquids and solids are either equal to 1 or we're ignoring them. Okay. Now, the one example we did in the last video, we did have to do an ice table because this goes to equilibrium, so we can use all of our equilibrium tricks with this. So what we're going to do is we're going to kind of pick up there and we're going to keep practicing. Now, the Ka values, I wanted to remind you, you can find Ka values in Appendix D of our textbook. You are not memorizing Ka values. That's not a thing that we memorize. You memorize the 7 strong acids. You memorize the 8 strong bases. You memorize what it means. It's a strong acid or a strong base, but we're not going to memorize the Ka values. Okay. So when we look at any calculation, now this, I kind of gave it away here, but the first thing we need to do when we read a problem for chapter 16 and 17 is look at the chemical and decide if the chemical is one of 4 things: a strong acid, a weak acid, a strong base, or a weak base. Okay, so I can look at the chemical carbolic acid, which is also called phenol. We need to decide, is it a strong acid, a weak acid, a strong base, or a weak base? Well, the fact that it has acid in its name and that it starts with a hydrogen are our clues that it is a type of acid. So it's either going to be a strong acid or a weak acid. So we would have to search our memory banks of those 7 strong acids. Dang, this is not one of them. So this is a weak acid. Okay. Once it's a weak acid, I automatically rename it HA because I don't care that it's carbolic acid and that's what its chemical formula looks like. It's a lot easier if I just call it HA. So since it's a weak acid, we're going to fall back on this information. We go to equilibrium. Okay, that's our equilibrium constant expression. We're told in the question here that the Ka value of phenol is 1.3 times 10 to the negative 10th. So now let's read the problem. Calculate the pH of a 0.30 molarity solution of carbolic acid, which is phenol, which again to us is HA, weak acid, at 25 degrees Celsius if we're given the Ka value. So we need to solve for pH. This is our equilibrium equation. We know we have the Ka expression, products over reactants, so we know we have that. But out of all of this, nowhere does it actually show pH in any of these equations. Well, which chemical that you see in this balanced equation that's right here, which of those 4 chemicals is most closely directly tied to pH? Hopefully you're thinking H3O+, because we have this beautiful equation that directly relates H3O+ to pH. So the question asks us to solve for the pH value. Well, as long as I can come up with the H3O+ value at equilibrium, I can convert that to pH. So what it's asking for first is to solve for the equilibrium value of H3O+, and then we can solve for the pH from there. The question does not give us the equilibrium value of H3O+. So when we don't have enough information in the question just to solve, we need to think about ice tables. So we know we have the Ka expression there, but I'm going to start with, so our equation again was Ka So H2O, equilibrium, H3O plus, A minus. Okay. Now, when I set up my ice table, I'm ignoring water because water is a pure liquid. So I'm just doing my squiggle line there to represent what the arrow would be. So we're going to have our initial row, our change row, and our equilibrium row, our ice table. Okay. So looking back at our question, we were given the pH of a 0.30 molarity solution of HA. So 0.30 is a value we were given for the weak acid. Well, that's the initial value. Okay. So I'm going to put 0.30 right there. So what do you think we're going to say the initial values of hydronium and A minus are? They weren't mentioned in the question, so they're going to be zeros. The question does not give us any equilibrium values at all, so I have no more numbers to put in here, but we can work on our change row. So the change row, we know that with ice tables, one side of the arrow is always positive and one side of the arrow is always negative. And the squiggly red line was my reminder of where the arrow is. So looking at this, the right-hand side is going to have to be positive because the initial value is 0. And so it has to, our final answer at equilibrium can't be less than 0. So I can't take 0 minus something. That would make it a negative number. That's not allowed. So it has to be pluses on the product side, which means a minus on the reactant side. Now the number of x's that we place in our change row has to do with the coefficients. Well, there's a 1 in front of HA. There's a 1 in front of H3O plus. There's a 1 in front of A minus. So this will be minus x for HA plus x and plus x for H3O plus and A minus. Okay, so we've done our initial row, we've done our change row. We don't have any numbers. We were not given any equilibrium values. So I don't have any numbers to put here, but we do know that the initial plus the change equals the equilibrium. So I can bring down this information and say for HA at equilibrium, it'll be whatever 0.30 minus x is. I don't know what x is yet, but I know that once I find it, 0.30 minus x will be it. And for H3O plus, 0 plus x will be whatever it is at equilibrium, and A minus 0 plus x. So I just removed the zeros. So my ice table. Well, my ice table is as done as it can be. I have no more numbers. But we're not finished with the problem. The question wants us to know the pH value, which means I need to know the H3O plus value. So I need to know, well, x. So in chapter 15, we ran into this dilemma before. What happened was we needed to solve for x, but our ice table didn't give us enough information. But we were given the Ka value. So just a quick reminder, the equilibrium constant expression, products over reactants, looks like this. And our Ka value was given as 1.3 times 10 to the negative 10th. So what I'm going to do is I'm going to substitute in for Ka, 1.3 times 10 to the negative 10th. And I'm going to substitute in for H3O plus at equilibrium, x. And for A minus at equilibrium, x. And for HA at equilibrium, 0.30 minus x. So I'm going to rewrite this. Where x times x, I'm just going to write x squared. Is it coming back to you? This is going to be quadratic formula time. So I'm going to take that 1.3 times 10 to the negative 10th is equal to x squared over 0.30 minus x. And what we need to do is get it in the format ax squared plus bx plus c. So I'm going to have to cross multiply. So 1.3 times 10 to the negative 10th times 0.30 minus x equals x squared. So I'm going to have to distribute and combine like terms. So I am going to skip some steps, okay, and put it in the form that I have up here, which is 0 equals, oops, I don't need to write ax squared again, x squared plus 1.3 times 10 to the negative 10th minus 3.9 times 10 to the negative 11th. So the a value is 1, the b value is 1.3 times 10 to the negative 10th, and the c value is negative 3.9 times 10 to the negative 11th. And that is our formula for the quadratic formula. Okay, so I would need to plug in these values. Now, I am going to do a magic arrow that says quadratic formula, where I plug those numbers into the quadratic formula and solve. Now, I get two values for x. One of them is going to be positive, and one of them is going to be negative in this situation. So I'm going to keep the positive one. 6.245 times 10 to the negative sixth. Okay, that's the value of x. So coming back over here, 6.245 times 10 to the negative sixth is the value of H3O plus, which is awesome. But the question asked us to solve for pH. So I guess I should change colors. It's getting confusing. Here's my new stuff. pH is equal to the negative log of H3O plus. So I'm going to grab my calculator. This has two significant figures, so my pH should have two decimal places. So when I do my math, I get 5.20. So at this solution, is it acidic, basic, or neutral based on the pH value? Well, it's going to be acidic because it's less than 7. Okay. So, quadratic formula. We did it. We survived. Everything's fine. But turns out there is a possible shortcut to let us avoid the quadratic formula sometimes. I didn't show you this shortcut in chapter 15 because we didn't come across any situations that met the criteria to do the shortcut. But if we look at our value of x, the 6.245 times 10 to the negative sixth, that's a really small number, 0.000006245. Okay. Now looking back at our ice table, that's what is the number here, and that's what is the number here. Now, I didn't do it because I didn't need to solve the problem, but if I took 0.30 minus that, so if I took 0.30 minus 6.245 times 10 to the negative sixth, I'm going to just get 0.30. Sure, my calculator says, oh, sorry, this is a fifth. What did I do on the other slide? Hold on. Yep, that was a big old typo on my part right here. I'm so sorry. This is a 5. That's a 5. So that's a 5 and a 5. My answer of 5.20 is the correct answer. If you were following along with your calculator, you got a different number, and it's my fault. Oh my gosh, no, it's a 6. I'm so broken. I was looking at the wrong problem again. It's a 6. I was right the first time. Okay. Never mind. Everything's fine. Sorry. Okay. What I was saying. If I take this back, 0.30 minus 6.245 times 10 to the negative sixth. What my calculator gives me is 0.29999 4. If I round that back to two decimal places or two significant figures, isn't it 0.30? So what that means is this x value is so tiny that taking 0.30 minus x is really just 0.30. X is so small that when I subtract it, 0.30 minus x, I don't see a change in the number when I apply significant figures. Okay, so this is my shortcut. That sometimes I can drop the trailing x, the minus x. Okay, if I did that, so I'm going to go through the math and then we're going to come back and talk about when you can do it. What that changes, when I set up my products over reactants and the equilibrium constant, it's just 0.30 on the bottom, not 0.30 minus x. So I can cross multiply, and then I can square root, and then I have a value of x. 6.2 times 10 to the negative sixth. Okay. I did not have to do the quadratic formula. That took me way less time than the first way. Okay. And then once I have my value of x, if I plug it in to solve for the pH, I get 5.20, and oh my gosh, that's the same answer I got when I did the freaking long quadratic formula thing. So that's a beautiful shortcut. Okay, so let's talk about when you can do this shortcut. You can only do this shortcut when your x value is really, really small compared to the initial value. Okay, like compared to the initial value of your acid when X is really, really small. Well, how do I know that? The only way I know when X is really, really small is when I do the quadratic formula and get my value of X, and then afterwards I know that, and that doesn't save me any time. So here's the rule that we're going to use. If your Ka, if your equilibrium constant value is a times 10 to the negative 8th or smaller, so times 10 to the negative 9th would be smaller, times 10 to the negative 10th would be smaller, times 10 to the negative 11th would be smaller. We can do this shortcut. And what the shortcut is getting rid of trailing x's. So once we get it at the equilibrium row, if we have anything something plus x or something minus x, not like these that are just x. We can't get rid of x then, because then that would be 0 or nothing, and that's not true. But it's just any what I call trailing x's, trailing after a number. We just get rid of that, leaving just the number, and that gets us out of doing the quadratic formula. Now, our textbook does not use negative 8. It uses negative 5. And you're like, ooh, I like the textbook better. Yeah, except with the textbook's way, you can do the shortcut when the equilibrium constant is negative 5 or smaller, but then once you're done, you have to stop and check to see if it actually was appropriate. They give you a way to tell if x is small enough or not. So then you have to do another calculation. And then if it's not, because sometimes at negative 5, negative 6, negative 7, sometimes you can't use this shortcut. So then after you did the shortcut, tested it, found out that it wasn't correct, you're going to have to go back and redo the whole problem using the quadratic formula. That's not worth it to me. So what I did was I drew the line at a place where it's always fine to use the shortcut times 10 to the negative 8 or smaller. So what we're going to do if something's times 10 to the negative 2, negative 3, negative 4, negative 5, negative 6, or negative 7 is not use the shortcut and just use the quadratic formula. Sorry, buddies. But that way you don't have to worry about, like, you did the problem and they got to check. Did it work? Oh, crap, it didn't work. I got to go back and redo the problem. To me, that was more annoying than having an absolute line. Okay. If you don't like this shortcut, you can do the quadratic formula every time. That doesn't hurt anything. The issue is, I told you guys in chapter 15 that on our test, I would have only one question that required the quadratic formula. When I say that, I'm taking into account the fact that if you can do the shortcut, you're going to do the shortcut, so that will not require you to use the quadratic formula. Okay, so if you're not going to use a shortcut, you might have to use the quadratic formula more than once. I don't say might. You will have to use the quadratic formula more than once when we take our test. Okay, so that's the downfall of not using it. So let's try another problem. What we need to do now is practice. Okay, so I went through every possible scenario that we've got. So what I want you to do is to read this question, and then I want you to try it. I want you to hit pause, and I want you to try it. And then I want you to hit play when you're finished, and then we'll go through it together and see how we did. So for this one, the first thing we have to do is identify the chemical. I'm going to get you started first, though, before you go off and do it. So niacin, the name doesn't help us identify it as a strong acid, a strong base, a weak acid, or a weak base, except for I know that it's not a strong acid and it's not a strong base because we have to memorize those, and that's not the chemical for any of them. I gave you the picture on purpose, because see him? Starts with the hydrogen. I know it looks like it ends with the hydrogen, but it's the hydrogen at the end. And so it's an acid of some kind. So you just have to decide if it's a strong acid or a weak acid. I really already gave you the answer to that, but once you decide that, I want you to try this problem. So why don't you hit pause now, try this problem. When you're finished, hit play, and then we'll go through the answer together. Okay, so I want purple. This chemical is a weak acid because it has an H in it, and it's not one of the 7 strong acids. So from now on, niacin is HA. Okay, we've identified that. A 0.020 molarity solution of HA has a pH of 3.26. We need to find the Ka value. Okay, so it's a weak acid, so we know it goes to equilibrium. And as an equilibrium constant expression. Okay, and we need to solve for Ka. So what I need is I need to know the equilibrium value of H3O plus, I need to know the equilibrium value of A minus, and I need to know the equilibrium value of HA. So when I do products over reactants, I can put those numbers in. We were given no direct equilibrium values. The 0.020 molarity, that's going to be an initial molarity, and then we were given the pH. Okay, so what I'm going to do is I'm going to go ahead and set up my ice table because I know I need an ice table. I don't have all the equilibrium values that I need. So I guess I should have written it over here. I'm going to rewrite HA plus H2O liquid equilibrium H3O plus A minus. Okay, and I'm going to do an ice table. And I do know that Ka is equal to products, which are H3O plus times A minus over reactants, which is HA. I'm ignoring water because it's a liquid. So in my ice table, I'm ignoring water. And plugging in numbers. Well, from the question, it told me that HA is 0.020. It did not mention either of these two chemicals, so I don't know their values. Okay. Now it told us a pH. Now I cannot put the pH into this equation. You can only put molarities into this equation. So the pH, though, is going to tell me information about H3O plus. So what I'm going to be able to do is use the idea pH is equal to the negative log of H3O plus. I'm going to place 3.26 in the pH spot. And then I'm going to solve for H3O plus. And when I did that, I got 5.495 times 10 to the negative fourth. This has 2 decimal places, so my molarity should have 2 sig figs, but I did not want to round yet. So this is going to be 5.495. So I didn't want to round, so I kept a couple digits. Okay, so I did that. All right, got an equilibrium value. Let's do the change row. So the change row, one side is going to be positive changes and one side is going to be negative changes. Well, this side has to be positive because it starts at 0. This one has to be minus. So X, I have 1 HA, so I have 1 X. I have 1 H3O plus, so I have 1 X. I have 1 A minus, so I have 1 X. So we do have one column that is complete. We know that 0 plus X equals 5.495 times 10 to the negative fourth, which tells me the X value is 5.495 times 10 to the negative fourth. And for HA, I'm going to take 0.020 minus X, which is 5.495 times 10 to the negative fourth. And when I did that, I get 0.194505. Okay. So the question has not been answered yet because the question said to solve for Ka. So what I need to do is plop my equilibrium numbers into my Ka expression. So products, H3O plus times A minus over, I guess I don't have to do parentheses for this, 0.194505. When I do this, I'm going to have 2 significant figures for my answer, and I get 1.6 times 10 to the negative fifth. Okay. We didn't have to do the quadratic formula, so that's good. All right. I want you to do one more example. I want you to try this one. The Ka for hydrosulfuric acid is 9.5 times 10 to the negative 8th. You're supposed to calculate the pH of 0.010. So hit pause, do the problem, and then hit play, and we'll go through it together. So first step is figuring out what type of chemical is hydrosulfuric acid. Well, it's got the word acid in it, so it's a strong acid or a weak acid. Sulfuric acid is a strong acid. Hydrosulfuric acid is a different chemical. So this is a weak acid. Okay, so this is a weak acid. So that means it's going to be HA. Since it's a weak acid, it's going to go to equilibrium, and I'm going to now call hydrosulfuric acid HA for the entire problem. So I'm going to write out this I know that Ka equals products over reactants, so H3O plus times A minus over HA. And we're supposed to solve for pH, which means I need to know the H3O plus molarity, and we are not given that. So I'm going to set up my ice table because I need to know the H3O plus molarity and I don't have it. So I'm going to ignore water. I'm going to do my squiggly line there. I'm just going to fill in the information that I have. Well, I do know the initial value of HA and the initial values for the other chemicals since they weren't listed. I can figure out the change row. This side's going to be plus and this side's going to be minus. There's one HA, so 1X, one H3O plus, so 1X, one A minus, so there's 1X. I don't have any numbers for the equilibrium row. So all I'm going to do is just take the initial row plus the change row. I'm just going to write it as expressions. And what we're trying to solve for, we need to know H3O plus so we can convert it to pH. Well, I don't know the value of X right now, and my ice table's finished. So I'm going to have to put this into the Ka expression. So before I go plug, words are tough today, my numbers in there, this is going to end up looking like it's going to be a quadratic formula problem, what's going to happen. So what I would like you to do is to check to see if you can use the shortcut. That's a -8. So our shortcut says if it's times 10 to the -8 or smaller. So what that shortcut means is we're going to get rid of trailing x's. So from now on, the equilibrium concentration of HA, we're just calling 0.010, not 0.010 minus x. So what that's going to let me do is for Ka, I'm going to plug in 9.5 times 10 to the -8. For H3O plus, I'm going to plug in x. For A minus, I'm going to plug in x. X times x is x squared. For HA, I'm going to plug in 0.010. So now I can cross multiply and square root, and I get a value of x of 3.082 times 10 to the -5th. I'm sticking with 2 sig figs with my multiplication and division stuff here because 9.5 has 2 sig figs, 0.010 has 2 sig figs. So that's the value of x. The question wants us to solve for the pH. Well, the pH is the negative log of H3O plus. H3O plus is x, which is 3.082 times 10 to the -5th. So 3.082 times 10 to the -5th. This has 2 significant figures, so my answer should have 2 decimal places. So I'm going to grab my calculator, plug it in, and I end up with 4.51, 2 decimal places. So is this solution acidic, basic, or neutral based on its pH? Acidic. It's less than 7. Doesn't that make sense when this is an acid? If you got a value of like 47, that would be really basic and that would be really wrong. So something would have went incorrectly. If you did the quadratic formula and you didn't use a shortcut, you should have gotten the same answer. Okay. Whew, deep breaths. The discussion worksheet will help. We're going to practice through all these things. The last thing before I let you go, polyprotic acids. So when they have more than one hydrogen. Okay. H2SO4 is the only one we've seen so far. Well, that you know that you've seen so far. This is a list of some of the polyprotic acids. So on that appendix D that has a list of the Ka values, you may have noticed that there are 3 columns, Ka1, Ka2, and Ka3. If you have an acid that has more than one hydrogen, it's going to have an equilibrium constant for every hydrogen. Because what happens is polyprotic acids, hydrogens are donated one at a time. So if we started with H3PO4, we added it to water, it would donate 1 hydrogen to make 1 H3O plus, and then the stuff that's left over. Well, that H2PO4, sorry, that would just be -1, is still an acid, so it can still donate. I didn't write those in the same order, but, and then HPO4, hydrogen phosphate, is still an acid. It still has a proton it can donate. So what happens is each of those hydrogens comes off in its own step. The first one, its equilibrium constant is Ka1. The second one, its equilibrium constant is Ka2. And the third one, its equilibrium constant is Ka3. So in that appendix D, if a chemical has a Ka1 and a Ka2, that means it has two hydrogens. And you can see that from the chemical formula. And it turns out that the first Ka, the first hydrogen that comes off, is by far the strongest acid or the biggest equilibrium constant by a factor of at least 1,000. So like if we look at ascorbic acid that has two hydrogens, it's Ka1. It's 8.0 times 10 to the negative third. That's a pretty big equilibrium constant for a weak acid. We couldn't use a shortcut on that. For the second step, it's 1.6 times 10 to the negative 12th. Well, ascorbic acid starts with two hydrogens. It gives one away easy enough because it already has another one. But when it comes down to it, that when it's got just the one hydrogen left, which is what is happening in Ka2, it's got one. It started with two, now it has one, and things are wanting it to give up that last hydrogen. So it goes from 1 hydrogens to 0 hydrogens. It's a tiny number, 1.6 times 10 to the negative 12th. That sucker's not sharing its hydrogen. That's its last one. So it's really difficult for these polyprotic acids to get rid of that last hydrogen because they've already given away at least one more. So we see that the Ka2s and the Ka3s get way smaller. We're not going to be actually calculating, doing problems with polyprotic acids. Here's an example of one that we could do that we're not going to, because this would require two ice tables. One for Ka1 and one for Ka2. So for this polyprotic acid, instead of calling it HA, it would be H2A for the first one. And then the second ice table would be HA minus. So we're not going to be doing these. I just wanted to show you that they exist. And if any of you are going on to take quantitative analysis, we're going to be best friends with polyprotic acids. So we will be doing the math with them. So practice, 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 my friends.